So today we're going to start looking at hyperbolic geometry, and we're going to settle in here for a while. And the hyperbolic geometry stems from the negation of Hilbert's parallel postulate, okay? So the negation of Hilbert's Euclidean parallel postulate, which we will abbreviate as such, which could be written the following way. So if you take a look at Hilbert's postulate, it says for every line L, and if we negate that, we've negated these things before. Maybe I should just make you guys negate it first and see how close you get. Let's do that. That sounds like fun. So take this paper. I hadn't thought about it till now, but it sounds like a good plan. Hilbert's parallel postulate is on the second one that's listed here. And I'd like for you to negate that statement. And we'll see if we need to make any edits to it. If you have a pencil, that's great. If not, you can scratch things out on your notes. So how did we start out? What did you write down first? The negation of for every line L. There exists. Good. So there exists a line L. The next part says, and every point P not on L. Well, what would that negate to? There exists, yeah. So we can actually use that phrase there exists and just kind of continue on. So there exists a line L and a point P not on L. So that's how I'll sort of write it down. Such that something happens. So what does it say over here happens? Not on L. For every point P not on L, what happens? It says there is at most one line M through P. So what would be the negation of there being at most one line M through P?
There are no lines.
There's what?
There are no lines.
So that's not the negation of at most. That happened on your test where a lot of people got that one backwards too. What does at most mean? No more than. So at most one would mean 0 or 1 actually. So what would the negation of that be? The more than part. So you could either change the at most to at least. I mean, that would be sort of the idea. But you don't want it to actually include that one possibility. So it would have to be at least 2. Does everybody say it makes sense with that? Or you can say more than 1. Either of those would be acceptable ways to do that. So I have written down such that at least 2 is what I have. And I'll put in the word distinct just for clarification, at least 2 distinct lines. They can't be the same, then they're not really 2 lines. 2 distinct lines are what? What's the whole kicker here? Well, back over here it said that most one line through P, line M through P, such that M is parallel to L. So that's the whole point still, right, is that I have more than one parallel line through the same point. So 2 distinct lines parallel to L passing through P. All right, so using that as a sort of jumping off point, we're going to take a definition and actually define what a hyperbolic plane is. So any Hilbert plane, remember Hilbert planes are neutral geometry, so any Hilbert plane satisfying the negation of Hilbert's Euclidean parallel postulate is called a hyperbolic plane. Your book actually uses a slightly different name for that. It actually calls it a non-Euclidean plane. So I'm going to talk about a few facts about hyperbolic planes. And the first fact is that in a hyperbolic plane, rectangles don't exist. These are facts about hyperbolic planes. So more generally speaking, what's actually true is that the negation of any statement equivalent to Hilbert's Euclidean parallel postulate is true in a hyperbolic plane. And the example is the one I just mentioned. For example, rectangles don't exist. We could talk about the triangles. The sum of the triangles is not going to be 180. We can talk about all these different, the converse to the alternate interior angle theorem is not going to be true. Okay? So all those statements are going to be the negation of them is what's going to hold in the hyperbolic plane. Second statement, any statement, or second fact, excuse me, any statement which is true in Euclidean geometry and false in hyperbolic geometry must be equivalent to Hilbert's postulate. And there's a very brief proof for why this statement's true, so we're going to do it real quick. To prove that this is true, we're going to let S be such a statement. Okay, so a statement that's true in Euclidean geometry, false in hyperbolic geometry, okay? Then what we're saying is that the hyperbolic equivalence, or the hyperbolic Euclidean parallel postulate, I didn't mean hyperbolic, and I said it twice, Hilbert Euclidean parallel postulate, having that statement true implies that we have statement S. That's what it takes, right? I got to be inside of Euclidean geometry. I've got the parallel postulate for Euclidean geometry. And by what we know about logic, then the contrapositive of that would also be true. So the negation of S would be implying the negation of Hilbert's postulate. But we also know that if we negate Hilbert's postulate from what we were given, right, that S doesn't hold. That's the other statement that this actually said. Thus, these two statements are equivalent. I have one more fact. I've run out of space on this screen. I've got one more fact for us about hyperbolic geometry at the moment. Number 3. Any statement which is true in both Euclidean and hyperbolic geometry is provable in neutral geometry. Which is where we spent our last 3 class periods, in neutral geometry. So a question I'd like to pose. Think about it for a moment or so. Here's my question. Do some, but maybe not all, lines have a unique parallel through points off that line. You see, what we just said a moment ago is that there exists a line that does this, right? We didn't say it has to be all lines. We just said there exists one. So the question is, does there really exist one, or is it really true that it's a more strongly worded statement than what we had before? Do you understand the question? So what do you think? Is it possible to have places in hyperbolic geometry where there is a unique parallel, even though there's not one everywhere? We should vote. We're not going to.
Can you rephrase the question?
Sure. So we know that there exists these locations where I have something that looks like, let's say, for instance, here's my line L, and here's lines M and N, both through P. And M and N are distinctly different. Obviously, they intersect, but they're both parallel to L. All right, this is what our hyperbolic postulate that we already said, like that initial statement that we began with this morning. So the question is, does it always happen like that? If I take a particular point P, will there always be more than one line through P parallel to L? Or are there some times when it's unique? Is there some time when there's really a line L and there's just only one line parallel to it in hyperbolic geometry? Shana doesn't think so. It seems like it would be odd if that were true, right? That it sometimes works and it sometimes doesn't. So there's actually a universal hyperbolic non-Euclidean theorem that says that. So you're right, Shana, good job. You are, you got it. I don't have space to draw. I've already drawn so much on the screen, so let me actually go over here. We're going to actually prove it too. This is the universal hyperbolic and your book uses the word, instead of hyperbolic, your non-Euclidean. So if you were looking at this, it would say universal non-Euclidean theorem. Okay. And it says the following, in a hyperbolic plane, for every line L, and every point P, not on L, there are at least two parallels to L through P. So I can't have both of these pictures happening, where the second one that I drew is a unique line that satisfies these conditions, but in the first one I have more than one line that would satisfy those conditions. If I'm going to have more than one line satisfy the conditions, some of the time it actually happens all of the time. Okay? Now, that's a much stronger statement than we actually made before, because I didn't say there exists, I said it always happens. So let's take a look at a proof for this particular theorem. And let me draw a picture to start with. Well, we'll draw it. I'll just leave a space for it, and we'll keep drawing it as I go. All right, step number one. We're going to let L be an arbitrary line. And P, not be on L. Okay, so we've got a point not on L. We've got the line L, and I'll draw it over here. So here's my line L, and here's my point P. That's the setup. And that makes sense, because that's the setup of the way it's describing it anyway in our theorem. We're going to drop a perpendicular PQ to L. And we can do that by proposition 316. Okay, so I know I've got a perpendicular right here. Our next statement then is that we're going to let M be a perpendicular to PQ through P. It's also proposition 316. So I've got this line M right here through P. And what I know is I know that it is perpendicular to PQ. All right. Then we actually know that M and L are what? What do you think M and L are from what you've learned before? They're parallel, yeah. So then M is parallel to L, and this actually occurs by the corollary number 1 to theorem 4.1, which theorem 4.1 is the alternate interior angle theorem, by the way. So we've got parallel lines now. So now we're going to let R be on L, and it's not Q. So I never labeled Q. There it is, and there's R. Okie dokie. So, and of course that's true because points have more than one line. That was an incidence axiom. I think it was IA1 that we did. I don't have that written down, but it's an incidence axiom. So it's there. And we're going to let T be the perpendicular to L through R. Proposition 316 coming up again, of course. So now I've got a perpendicular to here. Oh, and I should label it. That was T, I decided, right? Yeah. Okay. I think I'm just going to have to flip back and forth between my screens at this point. All right, we're on number 7. I'll flip back to the picture as we write things down. We're going to drop perpendicular PS to line T. Okay, so it's to line T through point P. And again, we keep using the same proposition because it keeps working. So proposition 316. Okay, so over here on my diagram, I've got this happening. It's a perpendicular. I know it doesn't look perpendicular, visually speaking, like we've been talking about, but work with me for just a moment, okay? I'm going to drop this perpendicular right here, and there's PS, and we're about to see why S can't be, if you will, right here. Any guesses? What would happen if S were actually perpendicular and on line M? It would be the same line. Why can't it be, though? Maybe let me redraw it and just imagine with you what would happen. Oops. Imagine that S is actually right here. And we're saying that we're taking PS and it's supposed to be perpendicular to M. What's the problem, Kelsey? It's a rectangle. And what's that problem with that? They don't exist. Do you guys see it? Yeah. Felipe's not convinced, but he sees it. Okay, so we have this line right here. It does have a right angle, but it can't be line M because otherwise we would have indeed a rectangle. So that's going to finish out our proof for us. So here's number 8. Then PS, as a line anyway, is parallel to L by corollary 1 again. And as we just said, S cannot lie on M. Otherwise, quadrilateral PQRS, yeah, got them in the right order, would be a rectangle. Thus, there are at least 2 distinct parallels through P. Namely M, and we created PS. Corollary to this, and a very brief proof for it. In a hyperbolic plane, for every line L, and every point P, not on L, before we said there are at least 2, right? Well, there are actually infinitely many, because we can just repeat this process again and again and again, which is exactly the proof too. So there are infinitely many. Parallels to L through P. And like I said, the proof of it is just that. We would just vary R in the previous construction. The last proof we did is what we would call a construction proof, because we actually constructed the image that fell apart, you know, so that's why they're calling it a construction right here. All right, so our two possibilities right now are one parallel line always exists through the point parallel to the other line, you know, if it's not on it, like that Euclidean parallel line postulate, right? And our other possibility is not really that there's at least two. I mean, it is, but we can be a lot more specific and we can say there are infinitely many parallels through every point not on a line. Those are our two possibilities now at this point. So what we're going to do is we're going to continue talking about some different images and how they end up sort of portraying themselves in different geometry and specifically in hyperbolic geometry. And we're going to start with triangles. That's a typo. Okay. So triangles in hyperbolic geometry. What do we know about them so far from our postulates when we did equivalencies? The ones you did for homework, the one I handed out in the note sheet too. What do we know about triangles? In Euclidean geometry, they add up to 180 degrees, and we know in non-Euclidean geometry, we know that they don't, right? That's all we really have as far as just negating that statement, is that they don't add up to 180 degrees. You're right, that's actually where I'm headed next, is that they're actually less than. So the theorem says the following. And to abbreviate, I'm going to call it HG so I don't have to keep writing hyperbolic geometry, okay? So in hyperbolic geometry, HG, all triangles have angle sum less than 180 degrees. And the proof looks something like this. It's proved by using the non-obtuse angle theorem. And just for reference, it's on page 185 of your book. And proposition 4.11, which is from page 175. To get this. Notice it doesn't give me a different number, right? It just says less than 180. There's lots of things less than 180. So that leaves it pretty open for what's going to happen next, right? And the question is then, how far off are we? Are we just a tiny bit off? Like, is it 179.9? Or are we a lot off? Is it 160? Do you see the question? Those are very different sort of scenarios. So there's actually a definition that talks about how far off we are. And it's actually called, that statement is called the defect. So the defect, in essence, the how far off we are of our triangle, ABC, has a notation. It's denoted delta. So a delta looks like an S with a curl on the end. That's how I think it looks anyway. And it's this of ABC. So delta ABC. And it is defined to be (180 degrees) minus what? What do you think we're going to subtract? Well, it is delta, so let me actually write it that way. That would probably be a little bit better even. So this is the delta of ABC. So it's going to equal 180 minus what? 3 what? There are, not 3 as a number, but there are 3 things that we would subtract. What was that, Felipe? The vertices. Well, not really the vertices, but we identify them that way. The angles, yeah. So we need to take off each of the angle measures, or you could say we need to subtract the sum of the angles, right? The defect is simply how far off of 180 we are. Are we way far away, or are we really pretty close? So if we were to take 180 and we were to take off the measure of angle B, you can write them in parentheses and add them together, or you can write subtracting them all off. So if you prefer, we could write it like that or like this. So we're going to subtract the measure of angle A, the measure of angle B, and the measure of angle C. And that's going to be called the defect, the how far off we actually are from the 180 that we would have had in Euclidean geometry. Worth noting, but a pretty obvious statement, we'll still write it down. The defect of every triangle in HG, hyperbolic geometry, is positive. Why? This sum is always less than 180, right? That's exactly what the theorem said. The sum's less than 180, and we're taking something smaller than 180 away from 180. Yeah. All right, corollary to this, to the theorem, that is. In hyperbolic geometry, all convex, I'll define that in a minute. Okay, so bear with me. I haven't actually defined that in class yet. Convex quadrilaterals have an angle sum less than 360. So I'm going to prove this, but let me define convex before I prove that, okay? A quadrilateral is convex if any line segment connecting any point on the quadrilateral lies inside. I'm writing it for quadrilaterals. There's nothing special about quadrilaterals. I could use any shape here to describe convex. I mean, I could be talking about something that's got curves and stuff even, and this would actually work, but we're specifically talking about quadrilaterals at the moment, so I'm defining it that way, but lies inside the quadrilateral. And I know visually speaking that you guys can do quadrilaterals, or you can look at shapes and decide if they're convex or not. I'll draw one at the top. For example, this shape is convex according to the description. It's because I can take any 2 points, I can connect them with a line segment, and it stays inside the shape. And if we were likewise going to draw something that would be not convex, i.e. this one would be not convex, the reason again that it's not is because there are points that I can take and connect them, and the segment that they connect with is outside the shape. And you've heard another word used for non-convex. We don't really use it that much in geometry, but you've used it in the past. What word is that word? What have you heard? Concave is the word that you've used. And I think that it doesn't occur in higher levels of mathematics simply because when we talk about concave, we mean something a little bit different. Think about your concavity issues with like calculus and stuff. So non-convex is a little bit more traditional of a phrase to be used for that shape. All right, so let's go back and let's actually prove the one that I just stated. In fact, I will copy this corollary to my next screen, or at least I'm going to try. Okay, so this was my corollary, and we're going to prove this, or at least talk about what the proof would look like via picture. Okay, so we've got this this convex shape. So draw it however you want to draw it. And we are wanting to show that this would be able to, or would be forced to have fewer than 360 degrees. Any ideas about how we could do that using the facts we had before?
Theorem we just proved about triangles.
Okay, how would you do it now?
Divide that into triangles.
Yep, you got it. So pick your flavor of how you want to divide this into triangles. I'll do mine vertically. You can do yours horizontally or diagonally or however what works for what you've drawn. And so what we know by corollary, or by, theorem, we didn't give it a number, but the theorem before is that this angle sum is less than 180, right? And we also know here that this is less than 180, and of course if you add two things that are less than 180 together, you're going to end up with something that is less than 360. All right, so direct application of the theorem from before. All right, proposition 6.1 is next. And it's going to go back to some between this language rather that we've seen before. So if D is between A and B, I wrote it like this. Then the defect of ABC is equal to the defect of ACD plus BCD. Okay, we have an odd number of people today. Right, yeah, because, no, we have even number because there are two people gone. All right, fantastic. So I want you to grab a partner. You can use the same ones if you have for the last time if you want to, but you need to grab a partner somewhere where you're sitting. And I would like for you to prove this, and then we will make sure everybody's on the same page. And I don't mean this kind of proof. That's not really a proof, right? That's proof by picture. That's not really a proof. Like, actually write down the details of how this would work out with numerically, so to speak. So why would the defect of 1 equal the defect of the sum? So you're going to start with a triangle ABC,
D's between the triangles.
figure out where D is and so forth, and figure out what to do. So there's my first picture for you that I'll draw, and then you can continue the picture from there. Okay, so one reminder, when you're trying to prove an equality, you can't use the properties of equality. So you can't sort of do something to the left and to the right, because that's a property of equality that would insinuate that you already knew you have an actual equation, an equality that holds, and that's what you're trying to prove. So even though at the end we're going to get I mean, in the end, it's not going to matter because you're going to get the same facts on the left and the same facts on the right. Do you guys remember when you were in trig? I don't know where that was, but do you remember in trig? Hopefully someone in trig told you when you were solving identities that you can't manipulate both sides of the equation, or maybe they let you manipulate both sides of the equation, but you can't sort of intermix the two sides of the equation, right? And the reason, again, is because you don't know that the equation is true. You're supposed to be proving that it is. Same property is present here. So let's take a look at what happens when we do this. I'm going to look at the left-hand side with you. I made some mentions with you guys as you were working about the fact that you have multiple angles D and multiple angles C, so you have to be a little bit careful on how you write it. You can't just write angle C. There's 3 of them. You can't just write angle D. There's 2 of them. So let's actually write all these down. So if we're doing the defect of ABC, the whole larger triangle, I'm going to use just A and B and C to be the large angles, okay? So on the left-hand side, I have 180 minus angle A, angle B, and angle C, and that I'm insinuating is the larger angle C. When I break it into smaller pieces, I'll be breaking them down, okay? On the right-hand side, then, I have the different smaller triangles. So I have 180 minus, well, I've got angle A still, right? So that's good. But now I've got angle C, and it's a smaller angle C, and I've got an angle D, and it's a smaller angle D. So angle C that I have for triangle ACD would be angle ACD specifically. Whoops. And the triangle's angle for D would be DAC. So that's the defect of ACD. Okay. And then we also have, even though I don't have space to write it on the same line, we're adding on to that the defect of angle BCD. Well, in angle BCD, B is one of the angles, so that's minus angle B. And then the C angle is actually angle BCD. And the D angle is angle DBC. Okay, so we can manipulate the left, we can manipulate the right, but we are not moving between the sides. Okay, just like in trig. So I have my 180 minus angle A. These are terrible. I should have measures of angles all over these places, but
Dr. Hans?
yes.
Does that need to be
Oops.
angle BDC and the one before needs to be ADC?
Okay, say that again, Seth.
So you have minus angle A, minus angle ACD, and then you have minus angle DAC. Shouldn't that be ADC?
Oh, yes, it should. Thank
And
you.
then-
Yeah, I've got them listed wrong. You're right. I've got it zoomed in. I was trying not to go back to my picture. I should have looked at my notes instead. Okay, give them to me in the right order. D's got to be in the middle. So ADC, and this one, D's got to be in the middle. So BDC. Yes, thank you. Appreciate that. Okay, on the left, nothing changes. So actually, you know what? Let's not do the left-hand side. Let's just simplify the right-hand side. All right, I've got 180 and 180. That's 360. I've got angle A and angle B. So, you know, those are already present on both sides now. And somehow I've got to make amends for what's left over. So when I take angle ACD and I take angle BCD, what is the combination of those two angles? Yeah, the overall angle C, right? ACB, which is angle C for what I listed before. And that's angle addition postulate. I don't think I wrote down the number for it, but we had seen that before back in instance geometry. And then when I take these two at the end, ADC and BDC, what happens? Right, they're supplementary so that they're 180 degrees. So this is minus 180. And then if you take that 360 and that 180 and you subtract them, of course you get 180. You've got your angle A, your angle B, and your angle C, just like you had on the left-hand side to begin with. Make sense? Nice. So we are on time. Okay, let me state the next proposition. We'll prove it next time because the proof's a little bit long. I don't think we have time for the whole proof with just 5 minutes left. But we'll do the proposition, so we'll have a place to start from. Our proposition is proposition 6.2. And it says the following. In hyperbolic geometry, if two triangles are similar, then they are congruent. Okay, so Haley said, wow, and Hannah said, what? That's different, right? I mean, that does not happen in Euclidean geometry, agreed? Similar and congruent do not mean the same thing in Euclidean geometry, but in hyperbolic geometry, they do. And we're going to prove it when we get together in class next time on Monday or on Tuesday, okay? So I'll leave you to just be in awe of this strange result that we are about to prove.